What's going on, guys? Today we're going to look at how we can implement auto-scaling of a Node.js application in a Kubernetes cluster. The idea behind this is that we can horizontally scale our application automatically based on predefined scalars like CPU usage and memory usage, so that when an increased load hits our system, we spin up additional instances and can handle that increased load. So let's jump right in and find out how we can easily implement auto scaling in a Node.js app. To get started, we're going to go to GitHub and go to a previous project that we created, actually my last video, where we implemented metrics inside of Nest.js and exposed those using Prometheus and actually had a Grafana dashboard set up to expose metrics from our Nest.js app. So I'll include a link in the description to this repository. This is where we're going to start off from because we of course need metrics to expose that to Kubernetes so that we can auto scale. I'm also going to include a separate branch here which will include the final project. So if you want to see the code in a finished state, you can check out that branch, and I'll include another link in the description. So let's go back to our repository here and let's go ahead and clone that Nest.js metrics. Okay, so we'll go ahead and cd into Nest.js metrics, and then let's just run a npm install to get all of our dependencies. And lastly, make sure we just start up the server here with npm start dev. So we'll start the server up and watch for changes, and we can see that the app is started successfully. So I've gone ahead and opened up the project in VS Code, and since we've already done the work of setting up this Kubernetes cluster in the last video, and so if you haven't seen that video, make sure you watch to catch up. We created a Kubernetes cluster where we actually Dockerized this application and was able to deploy it to a running Kubernetes cluster and actually get these metrics exposed and see them in a Grafana dashboard. And of course, we're using this Prometheus module here from Will Soto Nest.js Prometheus to expose metrics from our Node.js app. Now, when we set up our autoscaler for this application in the Kubernetes cluster, we're going to choose a metric to scale on. And in this case, I'm going to choose CPU usage to scale on so that when CPU usage of our app increases to a certain level, I want the autoscaler to start up a new instance of our application to handle with the increased load because CPU is increasing. So in order to actually trigger increased CPU usage in our app, I'm going to go ahead and open up our app.service, and we're actually going to do some work inside of this app.service right now because currently, as you can see in our app.controller, we're calling getHello, and all we're doing is returning a string. So this isn't going to be very CPU bound at all, and it's not going to really stress test our system. So in order to actually simulate some CPU usage, I'm going to go ahead and open up the terminal in VS Code here. Let's go ahead and pm install the Fibonacci package. And you probably guessed it, the Fibonacci package is going to allow us to compute Fibonacci sequences up to a certain number that we specify. And this is a very CPU heavy synchronous operation, which normally you don't really want to be doing in Node.js. You want to be doing more IO bound work. However, this is going to be a great example because it's going to allow us to increase our CPU usage heavily and let the autoscaler kick in. So now that we've actually installed Fibonacci, let's go ahead and import star as Fibonacci from the Fibonacci package. So instead of just returning a string here, now what we're going to do is call Fibonacci.iterate. And so this is going to generate Fibonacci sequences up to the number we provide. Now I actually want to be able to configure this via an environment variable, which is going to allow us to be very specific about how much compute we're actually using in the app. So let's just use process.env and we'll grab the Fibonacci environment variable that we can specify later. And then we'll say that if it's not defined, then we will just have a default here of 3000. And just to keep our types clean here, we'll change the return type here to number. And we'll do the same here in the controller. We'll change this to a number. So now if we go back to Postman and send off a GET request to that controller at localhost 3000, we'll send this request off and we can see the Fibonacci number returned and a bit of information including the number of iterations and how long it took, in this case 238 milliseconds. So this is great, and we have everything we need to actually trigger the autoscaler that we're going to create. Let's go ahead and actually rebuild our Docker image here. So now that we've actually added this, we're going to go ahead and rebuild the Docker image, and I'm going to call it mgwe nest.js metrics. You can call it whatever you'd like if you're pushing it to your own repository. Of course, make sure Docker is actually running on your system. And once we do this, we should see the image starting to be built. So once the image finishes building for you, we can then run Docker push to push the image up to the Docker repository that we created in last video. If you have your own Docker repository, feel free to swap that out here. So once you've pushed up the image, the next step is to actually be able to generate a lot of load against our application, because right now we can only send a single request to our server or our Kubernetes cluster, and that's not going to be enough to trigger the autoscaler. We need to generate a lot of requests over a sustained period of time, or better known as a load or soak test, so that the autoscaler will kick in and we can actually see it increase the number of pods that are running over time as load increases. So in order to do this, we're going to make use of a popular testing tool called Artillery. Now I'll leave a link in the description to the docs for Artillery where you can learn more about it. However, it's just a load generation tool that will allow us to send multiple concurrent requests against a backend at once and generate that sustained load. So to install Artillery, if you don't already have it, I'm going to go ahead and run npm install-g Artillery latest to install it on my system. Once you have Artillery installed, you should be able to run artillery --help and get the help docs for Artillery. So now that we have Artillery installed, let's go ahead and set up a configuration file that will tell it how to actually run. I'm going to create a new folder in the root of our project called performance, and inside we will have a simple artillery config.yaml, and inside of here we're just going to specify the bare bones for telling it how to actually reach our server. And to do this, we'll provide this config key, and inside of here we'll have a target, which will be the actual URL that we're going to hit. So to start off, we're just going to hit the local Nest server at localhost 3000, and then we have a block called phases here, and this is where we actually tell it how much load to hit the system with. So we can specify the actual duration of how long the soak test should last for. This will be in seconds, and in my case I'll specify 300 seconds, which will be plenty of time for the autoscaler to kick in and add more pods for us. Next, we're going to specify the arrival rate, which is going to be the number of virtual users, or in reality the number of concurrent requests that are going to be hitting the system at once. And then finally, we're going to specify a ramp to property here of 100, and what this does is it's going to say that over time up to this duration we should ramp this arrival rate up from 10 to 100 concurrent requests. So over time, the load on the system will increase linearly. So lastly, we're going to provide the scenarios key here, where we can provide a name. We can call this whatever we want. I'll just call this scenario trigger autoscaler. And we specify now a flow where we tell it which routes to actually hit. In this case, it's going to be that simple get route, which just lives at the root path of our server. So now back in our terminal, let's go ahead and start up our development server again using pnpm start dev. Make sure the application starts up, and then we're going to open up a separate terminal, of course, where we can actually use Artillery. And to do that, we're going to call Artillery run, and then we're going to specify the path to the configuration file. So I'm in the Nest.js metrics folder, and then we're just going to go inside the performance directory and hit that config we just created. So let's go ahead and run Artillery. We can see that the phase has started here with our duration as specified, and now if we go back to our terminal here, we can see our logging interceptor at work. We can see the requests coming in, and this will increase over time steadily. So this is great. We can see artillery actually generating concurrent load on our system. So let's go ahead and cancel this out. We don't need to be running this locally, of course. We want to emulate this same exact process inside of our Kubernetes cluster and actually implement our auto scaling. Keda is going to allow us to specify any number of custom scalars to tell Kubernetes when to actually scale. And so this takes care of a lot of the heavy lifting and complexity involved with the horizontal pod autoscaling in Kubernetes. It's going to make it really easy to specify our scalars. And so I'll leave a link in the description where you can learn more about Keda. So for now, all we're going to want to do is install this in our chart. So I'm going to create a new dependency here called Keda. And we're going to grab, in this video, version 2.9.0. And the repository here is going to be https://kedacore.github.io/charts. Let's open up our templates folder, and I'm going to create a new file in here called scaledobject.yaml. And so this is going to be the actual definition that Keda will receive to tell it how to scale. So let's build this together. We'll of course specify the API version like we do in any template. In this case, it's going to be keda.sh/v1 alpha1. And the kind here is going to be a scaled object. And so this is what Keda will use to actually create the HPA for us, or the horizontal pod autoscaler. We'll provide some metadata here, and like we do in most of these templates, we'll give it a name of the app here. I'll call it Node.js metrics, and we'll continue our labeling here. So I'll give it an app label of Node.js metrics as well. And now the bulk of this template, the spec here. Now we can specify a number of options. And like I said, I'll leave a link in the description to the full set of options where you can learn more. However, the most important ones we're concerned with is going to be the max replica count. So this is going to be the maximum number of pods that you're comfortable scaling to using the horizontal pod autoscaler. I'm running on my MacBook here, so I'm going to specify 5 pods as the max. And then we're going to specify the polling interval. And so this is going to be how often Keda is going to run our triggers that we're going to specify and actually check to see if it needs to be scaled. The default for this is going to be 30 seconds. In our previous video, we set up Prometheus to actually poll every 15 seconds. So to stay consistent, I'm going to actually set this to 15 seconds as well. And then the most important part of this spec here is going to be the scale target ref. And this is going to be the name of the deployment that we're going to scale up based on the triggers we will define. So of course, our deployment here is what we want to scale, the actual Node.js metrics application. So all we need to do is provide the name of the deployment we want to scale, and this will be Node.js metrics. Now finally, we can get to the actual triggers section here, which is going to tell Keda how to scale or when to scale. So I'm in the Keda docs right now. And so like I said before, there are a huge number of scalars available to us. So we can scale applications based off of Kafka topics, AWS resources, a whole plethora of different event-driven scalars here. The one we're actually concerned with is the Prometheus scalar. And this is going to be super flexible because it's going to allow us to scale applications based on custom Prometheus metrics. So essentially any Prometheus query you can think of that your system supports will be a valid scalar. And this is what we're going to use. So back in the manifest here, we'll specify the type of the scalar. Like I said, of course, it'll be Prometheus. And then we're going to give it the metadata here that it needs. So firstly, it needs the actual server address where Prometheus will be listening. So in our case, this is going to be the name of the service that Prometheus is listening under. And since this is running inside of our cluster, we can use the service name directly. So I will show you in a minute and verify. However, we need to be able to actually deploy this first. So let's fill this out. The name of the service is Node.js metrics Prometheus server listening on port 80. Next, we're going to specify the metric name here. I'm going to call it CPU usage. And then we have the actual raw query for this scaler. So again, we're going to review this query once we have our app running and we can actually see Prometheus directly. However, to get this running, we're going to enter the query in now. So the query is going to look like this. We're going to want to take the sum, open close parentheses, and I rate, open close parentheses, of the process CPU seconds total. Okay, and then we're going to specify the actual app we want to target here. Of course, this is Node.js metrics. And then finally, we're going to specify the range over the time period that we want to query, and this is going to be over 2 minutes here. And then finally, I'm going to multiply this by 100 so we get a nice percentage. So what this is going to do is it's going to give us the percentage of CPU that our application is using. And Keda will actually divide this by the number of running pods already to make sure that we actually get the true CPU usage per pod. And then finally, we can specify the threshold value here, which is going to be the value at which we do want to scale. So in my case, I'm going to say once CPU usage reaches above 50% on average for our pods, I want to scale up. So again, we're going to take a closer look at how we actually found this query in a second. But now we actually have all the metadata we need to deploy this. Now back in my terminal, I'm going to cd into the K8 folder and cd into the Node.js metrics. Now if you followed from the last video and you already have a deployment running, you can see it by running helm ls. I just uninstalled the project, and you can do that by running helm uninstall Node.js metrics to get a clean slate. So I'm going to run helm install Node.js metrics and provide the path to the folder. Now you can see here the installation failed because we're missing some dependencies, and that's because we added Keda. So we're going to run helm dependency update so that it's going to fetch all of our dependencies. And now finally we should actually be able to rerun that installation command to install our project. So now let's go ahead and run firstly kubectl get service. So I want to show you that service name earlier that we used for the server address here. This is just the name of the Kubernetes service that we have deployed here, right? Node.js metrics Prometheus server. And of course, it's listening on port 80. So that's why we specified the server address here. Next, let's actually get the node port for our Grafana dashboard. So in this case, 30010, and I will enter the username of admin. And if you remember from last video, in order to get the password for Grafana, we can run this command here, get secret, and then output the JSON path and base64 decode it. So you can run this in your cluster to get your password. I'll copy this and we will log into our Grafana dashboard. Now, just like we did in the last video, we'll add our Prometheus data source here under settings, add your Prometheus data source, and this is going to be the same thing we specified in the Keda configuration. We're going to pull the service name for the Prometheus server here and throw in port 80 so Grafana knows where to look for Prometheus, and we'll save this data source. And let's go back, and as we did in the last video, we're going to import this Grafana dashboard here using the ID of it. So it's 11159. We'll load this Node.js app dashboard and we'll use the Prometheus data source. And I just want to show you how I actually generated this query here. So all I really did was I went to the dashboard here and I found a metric that I wanted to scale on. So in this case, process CPU usage, and I just clicked it and went to explore here. And what this does is it actually shows you the raw query that's used to generate that dashboard. So you can see here, this is the same query we're using. It's irate for the process CPU seconds total, and I just swapped the instance out for the app name. So you can do this same strategy for any dashboard that you want to scale on. So if you wanted to do event loop lag, for example, you could click explore, get that Node.js event loop lag seconds Prometheus query, and you could plug that directly in to the query here, which is what makes this so powerful. Okay, and so finally, if you'll notice from last video, I made a mistake. I didn't actually create a service to expose our Nest.js metrics application. So let's go ahead and fix that now. I'm going to create a new terminal, and I'm going to run kubectl expose deployment Nest.js metrics, and we're going to specify the port we know is 3000 for our app. I'm going to specify the type should be node port because I want to be able to access this from localhost. And then I'm going to run dry run equal client, and I'm going to pipe this to a service.yaml file. And lastly, make sure you use -o YAML here to output this in the YAML format. So now we actually have a service manifest here all filled out for us that we can use to deploy and expose our Nest.js metrics app. So I'm going to just move this into our templates directory and go back to our terminal here, and we can run helm upgrade Nest.js metrics dot to upgrade our application with this new service. And then if we run kubectl get service, I should expect to see this newly created service, Nest.js metrics. It's a node port, and we can get the node port here, 32089, and access it on localhost. So to test this out, we should be able to just open up Postman and now send an HTTP request at 32089. And if we go ahead and send this request, we get an error, socket hung up. So this means that our pod is not actually listening for our connections. Let's investigate this. We're on kubectl get pod, and you can see by default here, we actually don't have a Nest.js metrics pod running. We have one that's actually terminating. So let's go ahead and actually run kubectl get scaled object, and this will be the scaled object that we just created. So we can see here that by default, we actually don't have a minimum number of pods that we want running. So let's change this by going back to our manifest here, and let's specify a min replica count of 1 now. And then I'll go ahead and run the helm upgrade Nest.js metrics command again. So we upgrade this scaled object. And now if we run kubectl get scaled object, and we can actually go ahead and run a describe on this scaled object just to get a bit more information about it, see what it looks like. And importantly, you get some important information here when you describe the scaled object. It can tell you if things are not working properly. So if we scroll up here, we can see the status of our scaled object, and we can also see the current scalar that we're using. And importantly, we want to look for this status of happy for the scalar, which means it's in a good state. And we can see here some more conditions that tell us that the scalar we set up, the CPU usage scalar with this query, is defined correctly and is ready for scaling. So what this scaled object actually does is, of course, if we run kubectl get pods, we can see we have 2 new pods running, a Keda operator and a Keda operator metrics API server. So these are going to work together with our scalars to create a horizontal pod autoscaler that will scale our application based on the scalars we define. So if we run a kubectl get HPA, we can see we actually have an HPA that was created for us by Keda. And importantly, we see the min pod, max pods, and our target of 50% CPU usage here. So we actually have a HPA all set up. So now if we go back to Postman, send off a request, we can see we get a response back from our pod in this Kubernetes cluster, which is great. So we're finally ready to actually start launching requests at our Kubernetes cluster to our pod running, and that has the horizontal pod autoscaler correctly configured now to scale up when it receives load. So the final step, let's go into our artillery config here. And of course, we're going to change the port out here for the port that our node port is on. In this case, for me, it's 32089. And you're going to go ahead and just change this out for whichever node port you're assigned. And then we should be all set to trigger this test. Okay, and the final step before we actually execute the test, I'm going to go ahead and edit our deployment, Nest.js metrics. And if you remember from before, we actually added an environment variable to define the number of Fibonacci sequences we want to run. Now I'm going to start off at a lower number here and actually define a new environment variable section here. We'll provide the name here for the Fibonacci environment variable that we want to run. And I'm going to give it a value here of 1,000 to start. So 3,000 might be a little too high. So we're going to start off at 1,000 here. And of course, make sure that 1,000 is actually wrapped in strings. 1,000. So we'll go ahead and save this deployment. So we'll go ahead and wait until the new pod is up and running. So once our new pod is up and running with that Fibonacci environment variable of 1,000, we're going to go back into our terminal here, and we will actually run the artillery run command again, where we point to the configuration file. So we'll go ahead and kick off this test, and we can also just check the logs real quick by running kubectl logs, enter the pod name and follow, and we should see a bunch of requests starting to flood into our server here. And then I'm going to go back to our Grafana dashboard here, where we actually get metrics about the process CPU usage. I'm going to look for the last 5 minutes and make sure we update this dashboard every 5 seconds. And we should expect to see the process CPU usage start to steadily increase as the number of virtual users in our artillery configuration increase and the load on the server is increasing as well. And so that's going to be important so that we actually trigger the horizontal pod autoscaler, and we can actually watch this in real time by running kubectl get HPA -- watch and take a look at the number of replicas that our HPA is currently set to. So bear in mind this may take a few minutes for the metrics to appear in your dashboard and for the HPA to start scaling. So it only took a few seconds for me actually, and we can actually now start seeing the CPU usage jump up here to about 30% as the number of Fibonacci sequences we're generating is slowly increasing. So after the next refresh window, we can see the CPU usage is finally cracking that threshold we've defined of 50%. Okay, so finally after a minute or two, our CPU usage is hovering around 70% or so here. And now if I run a kubectl get pod, you can actually see that our horizontal pod autoscaler has added an additional pod. And if we run kubectl get HPA, you can see that the new replica count is 2. So if we actually run kubectl describe HPA and enter the HPA name in, we can see we have a successful rescale event that hit it, and new size 2, reason, external, metrics, Prometheus CPU usage is above the target. So we can see the horizontal pod autoscaler working exactly as we have configured it, and by adding additional pods here, we're going to offload the number of requests that go to a single pod and make the requests finish in a faster time and deal with the load in a better way, which is exactly what we want to do. So I hope this tutorial has been helpful for you, and I will see you in the next video. Thanks and have a great day.